Friends, welcome back to ElectriVerse, where every spark tells a story. This is Series 5 SD Part 5, and today we are entering the most advanced, most powerful, and most misunderstood zone of the variable frequency drive, sensorless vector control. This is the technology that industries use every day, but most engineers do not know its true logic, its internal model, nor how its behavior works. Basic V/F control and the protection topics of parts 3 and 4 are one side. Sensorless vector control is a whole different world. Today you will become an expert in VSD and a true motion control specialist. So, let's get started. First, let's understand, why is a sensorless vector necessary? V/F control is simple, but the problem is that there is no real torque control at low speeds. The motor becomes weak when the load changes, the speed decreases. The dynamic response is slow, but industries need precise speed, instant torque, stable performance, strong torque at low speed, overload, handling precise movement. Without using an encoder, achieving all this seems impossible. But that is what makes the magic of sensorless vector control. Sensorless vector control is based on a brilliant idea. It creates a digital twin of the drive motor. That is, an internal mathematical model of the motor which is continuously simulated within the drive. The drive continuously estimates rotor speed, rotor flux torque, slip and load, inertia, magnetizing current torque producing current. There is no real-time communication between the drive and the motor, but the drive predicts what the motor is doing. And this estimation is the essence of sensorless vector control. Within the induction motor, there are two currents. First, the flux current, magnetizing current, which creates the magnetic field. Second, the torque current, which produces torque in VF control. Both currents are mixed. The inverter gets confused. And what happens in the sensorless vector? The inverter separates these two currents. Just like in a car, the accelerator and steering wheel are different. Similarly, in the motor, flux control and torque control are separated. Result: quick torque, smooth operation, stable speed, maximum power at low speed. Flow and torque both act as vectors in 2D. Motor control determines the angle of these vectors, the angle at which flow and torque align. The motor operates more quickly and strongly. That is why it is called field-oriented control. And since there is no encoder, the controller must estimate everything. That is why it is called sensorless field-oriented control. The most important element of the brushless vector is flux observer, flux estimator. The flux observer calculates the rotor flux intensity, the rotor flux angle, how much load is being applied, the motor speed, the magnetic field direction. Without all these, vector control is impossible. The flux observer within the drive continuously monitors the motor's behavior and estimates at what speed the rotor is turning and how much torque demand there is. An induction motor reality is the rotor speed is always behind the stator field. This difference is called slip. In sensorless vector control, the motor slip is calculated based on measured current, estimated flux, supplied voltage, motor resistance, motor inductance. The slip calculation will be accurate and the predicted rotor speed will be precise. And when the speed estimation is accurate, the vector control will be robust. Torque depends on the motor flux, the current that produces the torque, and the machine's design constant. In sensorless vector control, torque is not measured directly. Instead, what does the inverter do? The inverter estimates the motor current and flux, and by using both, obtains the exact value of torque. The inverter checks every millisecond. Current producing the torque, magnetizing current, which generates the motor flux, the angle or direction of the flux, the load reaction on the motor. By combining all these data, the inverter calculates the motor torque with high accuracy. Thanks to this scientific method, sensorless vector control provides very smooth, stable, and powerful AC motor control, even at low speeds. Sensorless vector control is powerful but not perfect 100%. especially at low speeds. When the motor runs very slowly, around 2 Hz, the magnetic flux inside the rotor decreases significantly. For this reason, estimating flux and torque in the inverter becomes difficult. Usually, at low speeds, this behavior can be observed. Torque may be somewhat unstable. Speed may oscillate slightly. Shaking may occur during startup. Say a heavy load is applied, the motor may stop. To control this problem, the inverter particularly adjusts functions such as torque boost and slip compensation to keep performance stable at low speeds. All of this is completely normal behavior. There are no faults or problems in the motor. This is just a natural limitation of the sensorless vector algorithm. The high-speed drive pair uses advanced logic known as field weakening. In normal operation, the motor flux remains constant. But when the speed reaches very high levels, the flux is slightly reduced so that the motor does not exceed its mechanical limit. Field weakening offers benefits such as achieving higher speeds, keeping the motor safe, avoiding current overloads, and maintaining controlled torque. This technique is also used in aircraft propulsion systems, electric vehicle motors, and high-speed industrial machines to maintain stable torque and protect the motor at high speeds. Sensorless vector control only understands real power when the load on the motor changes suddenly. A common example could be a conveyor belt that suddenly stops, a sudden increase in pump load, a high demand from the compressor, the load swing on a crane. As soon as the load changes, the inverter responds instantly. In every microsecond, the inverter checks parameters such as required motor torque, slip, flow, motor current, reaction to load. By analyzing all this, the inverter immediately increases torque to prevent the motor from stalling and to ensure the process continues smoothly. This behavior is very similar to that of a DC motor. Controlling an AC motor, as if it were a DC motor, is the greatest strength of sensorless vector control. Sometimes the sensorless vector fails. The reasons can be 1. The motor is extremely old. 2. Incorrect motor parameters were entered. 3. The cable is very long. 4. Heavy. Starting load. 5. Very low speed is required. 6. Flux observer mismatch. 7. High noise/harmonics level 8. Stuck shaft condition. 9. Broken bar in the rotor. 10. Weak ground connection. In these cases, the inverter gets confused about what the actual rotor speed is and how much torque is needed. Therefore, during commissioning, the motor parameter input is the most critical step. Acrónimo: Drive me is a function. Auto-tune. Auto-tune measures resistencia del estator, inductancia de fuga del estator, inductancia mutua, corriente magnetizante, constante de tiempo del rotor, parámetros de pérdida de hierro, flux behavior. The more precise parameters there are, the more accurate the speed prediction and a stronger torque will be obtained. Let's understand a real story from the field. A sensor of a heavy conveyor belt was operating in vector mode without a sensor. When the load suddenly changed, the belt slowed down, the motor overheated, and the inverter repeatedly tripped due to overload. After investigation, it was found that the actual problem lay in the inverter configuration. Some main issues identified were: the motor parameters were incorrectly set, the auto-tuning process was skipped, the torque limit was too low, slip compensation was disabled, the required flow level was very low, the motor was lifting heavy loads at low speed, and the cable was excessively long. Then step-by-step corrections were made, such as the auto-tuning was fully executed, torque boost was enabled, proper slip control was activated, flow optimization was configured. Low-speed stabilization parameters were adjusted, load inertia was correctly configured. The result was remarkable. The machine became smooth, torque was strengthened, overheating was eliminated. The operation of our has become completely reliable. Sensorless vector control in the VSD interview is my favorite topic. Some powerful questions. 1. ¿Cuál es el propósito principal del control vectorial sin sensor? 2. ¿Por qué el control sin sensor es inestable a bajas velocidades? 3. ¿Qué hace el observador de flujo? 4. ¿Cómo se calcula el deslizamiento? 5. ¿Cómo se estima el par sin codificador? 6. ¿Por qué es importante el autoajuste? 7. ¿Qué es el debilitamiento del campo? What are the sensorless failure cases? What impact does cable length have? What problem arises with heavy starting loads? If you answer these confidently, the interviewer will consider you a next-level engineer. Friends, this was part 5 of the VSD series, a complete masterclass on sensorless vector control. Today we learned digital double of the motor, flux observer, slip calculation, torque estimation, low speed limitations, field weakening, dynamic response, automatic tuning, fault cases, interview level clarity. In part 6, we will delve into even more advanced zones: closed loop vector control, encoder feedback, position control, and high precision speed loops. If you found this video valuable, like, comment, and subscribe to ElectriVerse. You have been watching ElectriVerse, where every spark tells a story. Stay charged, stay safe, stay happy.